Welcome viewers. In this video we will see the initial condition in network elements, this capacitor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic capacitor. What is the initial condition while applying the voltage, while switching, before the switching, after the switching? What is the initial condition in the capacitor? Let us consider the capacitor C. In this, the current flowing through the capacitor is IC, voltage across the capacitor is VC. The relation between current and voltage across the capacitor is IC equal to C into dVC divided by dt. So this is the current flowing through the capacitor. IC equal to C, capacitor into voltage, dVC divided by dt. If the DC voltage is applied to the capacitor, dVC by dt become 0 as the DC voltage is constant. Suppose if you apply the DC voltage, then this term dVC by dt become 0 because the voltage is constant in case of DC, right? So based on that, with respect to the time, the DC voltage is constant with respect to the time. Hence the current through the capacitor is 0, IC becomes 0. Thus, as far as DC quantities are considered, the capacitor acts as a open circuit, right? So, IC equal to C into dVC by dt. This term dVC by dt is 0 as DC voltage is constant with respect to the time. So that the current flowing through the capacitor is 0. So, for the DC quantity, the consider capacitor is act as a open circuit. So if you apply the DC quantity, the capacitor act as a open circuit. Now we can express the voltage across the capacitor in terms of the current. Earlier we discussed the current through the capacitor IC. By rearranging that equation, VC equal to 1 divided by C integral IC dt. So this is the voltage across the capacitor. The terms are rearranged with the limit VC equal to 1 divided by C integral minus infinite to T IC dt, right? So the charging from minus infinite to time T. Splitting the limit of integration. So we can split the limit VC equal to 1 divided by C integral minus infinite to 0 minus IC dt plus 1 by C 0 minus to T IC dt, right? So minus infinite to T is splitted into minus infinite to 0 minus to T. Now we'll see what is the minus infinite to 0 minus. The first term denoted as VC 0 minus, right? So this term can be expressed as VC 0 minus, that is before switching, right? At T0 plus, the equation is given by VC 0 plus. So this is the VC 0 plus equal to VC 0 minus. Minus infinite to 0 minus is expressed as voltage across the capacitor before switching plus 1 by C integral 0 minus to 0 plus IC dt, right? So this equation is now rearranged as VC 0 plus equal to before after switching equal to voltage across before switching plus voltage 1 divided by C 0 minus to 0 plus IC dt, right? Now we'll see what happened further. So as switch act in 0 time, the integration from 0 minus to 0 plus is 0. So this is 0 minus is before switching, 0 plus is after switching. So we consider that this is 0 time. There is no time delay between before switching and after switching, right? So that 0 minus to 0 plus is 0. There is no 0 time. There is a switch is act as a 0 time. There is no delay between before switching and after switching. So that above equation VC 0 plus equal to VC 0 minus. The second term is 0, right? That is the integral between 0 minus to 0 plus is 0. Thus, the voltage across capacitor cannot change instantaneously. Before switching, after switching, the voltages are equal. That is the conclusion we got from the above equation, right? So the voltage is cannot changes instantaneously, right? Now we'll go for the further analysis. In the network, if uncharged capacitor is present, then the current start flowing through it instantaneously when excitation is given to the network. Suppose if the uncharged capacitor is available, mean it will start charging, so the current flowing through it instantaneously when the excitation is given. So at the instant t0 plus, that is after switching, capacitor acts as short circuit. Once get charged at t equal to infinite, in steady state it acts as a open circuit, right? So uncharged capacitor is available, then it will current start flowing through it instantaneously when the excitation is given. So at t0 plus it acts as a short circuit. After fully charged at t equal to infinite, it acts as a open circuit, right? So that is the conclusion we got. If initially capacitor is charged to the voltage V0, earlier uncharged, this one initially charged before switching, then at instant t0 plus, 0 plus means after switching, it acts as a constant voltage source, because already charges is available, it will start discharging, so it acts as a constant voltage source of value V0, right? So the already is charged, the capacitor is charged at V0. While in steady state at t equal to infinite, it acts as a open circuit in series with the voltage source, right? So earlier this uncharged means while charging it acts as a short circuit, after fully charged it acts as a open circuit. If it is already charge is available, means it acts as a constant voltage source, because already charges are available at t equal to 0 plus. At t equal to infinite, after fully at a infinite value, it acts as a open circuit in series with the voltage source, right? Because of fully charged voltage source is there, at infinite it acts as a open circuit in series with the voltage source. So in this video we discuss about what is the initial condition of a capacitor. When it is connected across the DC source, this acts as a open circuit, because dVc by dt is 0. So totally the current flowing is totally 0. Then for other cases, when it is fully already not charged, uncharged means it acts as a short circuit initially, after fully charged it acts as a open circuit. If already charged is available, initially charge is available, means it acts as a voltage source, constant voltage source, thereafter it acts as a open circuit in series with the voltage source. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.